but he said it might be tricky.
All right. Hi, everybody. I hope everybody had a good weekend. I see lots of people submitted their written homework assignments. So I'm looking forward to going through those. I know I had good communication with a lot of the groups working on those, and I think the group assignment. This is my first time actually assigning this as a group exercise, and I think there's some things to work out, but I think in general it worked well. So I'll be trying to grade those assignments and getting that back to you probably by the beginning of next week. I might need the weekend to knock out that grading. Other things coming due this week. So we're going to cover Chapter 5. Chapter 5 is a fairly short chapter introducing the idea of forces. So we'll probably just spend 2 days on it, today and tomorrow, talking about Chapter 5. And then we are going to use whatever time we need remaining to finish that discussion on Wednesday, and then we'll introduce Chapter 6. So things coming due, your online homework for Chapter 5 will be due on Sunday, along with a pre-lecture for Chapter 6 that'll be the focus for next week, really digging into the details of doing force analysis. I've had one other announcement that I'll send a follow-up email around later this week, is that I've had a lot of requests for deferring or delaying some portions of the homework for various interruptions. And you know, there are a standard set of reasons why you might need an exception, you know, medical illness or a certain type of personal issues that you're having that come with documentation that we're required to accommodate by the university. But I also recognize that things are a bit chaotic with people's schedules. So what I did last semester was allow people to defer or postpone one assignment with no questions asked. Just notify me of that, and I'm happy to delay the due date at some agreed upon point for one of your online homeworks during the semester, if that helps you guys out with some flexibility. I do just ask that you communicate that with me as soon as possible. I'll send a note around. I think last year that handled 99% of the issues that came up. So hopefully that'll be the case this semester as well. So if you've contacted me recently and I haven't got back to you, I'll probably respond that I'll accept your request under this policy. And anyone else needing to do that, please don't hesitate to reach out to me. Okay, are there any questions or comments people have about homework or what I just announced there? Like I said, I'll send something, I'll send a message around with official details later this week. If not, then why don't we go ahead and jump into discussing Chapter 5. So let me get my screen sharing going. So Chapter 5, before I jump in and we talk about the summary material here, I just want to go through, and this might take most of today, just a discussion about what forces are and try to kind of build up your experience or your intuition, let's say, for what we mean by forces and what forces do to objects. So when I ask, maybe you guys can write your first thoughts that come into your head. When I ask you, what is a force? What do you guys think about? What is a force? You can either type it in the chat, or if you want to share your idea. Okay, a lot of you are saying pushing or pulling, a push or a pull. Okay, and I think that's right. That's the kind of standard thought that you want to have when you're thinking about a force. Is it's a It's a push or a pull on some object. So if I were to imagine, say, a scenario here where let's just inject ourselves into this situation to get a bit more intuition with it, where, so here's one person and maybe there's another person here, and this person, normally I do this as a demonstration in class, but this person number 2 is reaching out and leaning on or pushing on person number 1. Okay. Now, which of those 2 people is experiencing a force? What do you guys think about that? Okay, person 1, most of you are saying person 1 is experiencing a force. If I ask this individual, hey, what's happening? He would say, oh, something's pushing me. I'm being pushed. There's a force acting on me. And how does he know that? Because he was standing there happily at rest, v equals 0. And then suddenly his velocity changed, right? If he gets pushed, he gets, right, jarred back and he gets moved. So he's saying he's being pushed. What about person 2? Are they being pushed? What about person 2?
There's the resistance. Like,
yeah, this person 2 is pushing, right? Let's imagine that suddenly the individual 1 vanished from the problem. Okay, let's imagine this person magically disappeared while the actions of individual 2 stayed the same. What would happen to person 2 if that happened?
they would stumble.
They would move forward, right? They would suddenly gain a velocity in this direction. Okay. So what does that mean? That means that this person, right, by nature, right, without the interaction with a secondary object, this person would have a velocity that would be in this direction, right? They're trying to move in that direction. And then they encounter person number 1. And what that does is it applies a force backwards on person number 2 and slows them down, right? From person's number 2, they might not be pushing on that person like as an active aggression, right? Maybe they had a blindfold on and they were just trying to walk forward and they, with their hand out, and they ran into person 2, they would definitely say something pushed back on them. The wall pushed back on their hand. Because something impeded their speed. Something forced them to change their velocity or their trajectory. So in reality, both of those actors in this problem feel a force. Person number 1 feels the force of person number 2 pushing on him, trying to move him off of his initial velocity or his tendency to stay at rest. And person number 2 we could think about was, say, is trying to move forward, or they could have been walking into this person and suddenly they feel a backwards push that's slowing them down. And we're going to see that this is not an exception to the rule, but the law of forces. One of Newton's laws says that forces come in interaction pairs. That in order to have forces acting on objects, I need multiple objects. I need 2 objects acting on each other. A force is somehow exchanged between 2 objects. And if one of the objects in that system experiences a force, the other object experiences a force. And we're going to see as we move along here that the force that those 2 objects experience are equal in magnitude, but opposite in direction. Right? This guy, for instance, felt a pushing force. So he felt a force, like something was pushing him in this direction, whereas this guy felt like there was a force or something resisting his tendency to move forward. They're both feeling that force pointing in equal and opposite directions here. Okay. Let's think about some other examples that we might have some experience with. Let's imagine that I have another person here, and now the person is holding on to a spring. Okay, so he has a spring here that he's holding between his hands, and Okay, what we could see is that, let's say that if he wasn't holding onto that spring, the spring would have a length that was much smaller. It would be very compact, something like this. So this would be the spring at rest. Okay. And then the person's grabbing either sides of the springs and they're pulling it out, right? They're pulling it out. What would that person say that they're feeling the spring doing to them while as they stretch that spring apart? What do they feel that spring doing? What's it doing to their hands? Can you imagine if you're pulling on a spring, what do you feel on your hands? What's the spring doing? Yeah, it's pulling on their hands. Okay. That spring is providing a pulling force, right? It's providing a force in like this that's trying to take your hands, right? The only reason you're able to hold it out is because you're using your muscles to apply an outwards counter force. But if you were to totally relax your arms, what would happen is those arms that were at rest would change velocity and get pulled inwards by that force of the spring. Right? So you have some intuition for this, that if you see a spring stretching, right? If you see a spring and you see it gets disturbed from its equilibrium position, right? Its shape is changed. You know, it tries to restore itself to its original shape, and you can imagine holding onto that spring and it pulling your arms together if you were to relax them. Again, what is that force doing? If I have my arms starting at rest, right? And I let go, and I don't let go of the spring, but I relax my arms and keep holding on to them, that spring is going to cause my arms to suddenly gain a velocity and pull them inwards, right? Again, it's going to change the velocity. So we see this thing coming up here that forces, I know that there's forces because it causes velocities to change. And we've talked about the physical property that describes changing velocities. That's an acceleration. So forces can cause accelerations. Right? If there's an unbalanced set of forces acting on an object, it causes acceleration. It causes accelerations here. Okay. So what about this? You can imagine what's happening when you're holding the spring. Now let's imagine that I have a ceiling here, and what I do is I take and I hang that same spring that I was pulling on from the ceiling. And what I'm going to do is I'm going to hang, say, hang a box or some heavy mass from this thing here. Okay. And again, we can see the spring is stretched out. So what can we say about that spring? What is it doing to that box that's hanging there from that spring? What's it doing? Well, it looks the same as, right, this situation here. I see a stretched out spring there. And in that case, when I was pulling it, I know that, right, it was providing a pulling force inwards at either end of this spring. So that spring is pulling up on that mass. The spring is also pulling down on the ceiling, right? And there's some other forces acting on this thing. There's also force of gravity pulling down on this guy. And the reason that box can stay at a fixed position is because these two forces counteract, but that doesn't mean that there's not this upwards pull of the spring, right? So when I see a stretched out spring, I know that that means that it's pulling whatever it's attached to inwards at those 2 points here. And you can kind of imagine replacing, you know, your hands for the box and the ceiling, because it's the same phenomenon as what was happening to our stick man over on the left-hand side. Now, what's going to happen if I replace that string with just if I replace the stretchy spring with a string? Okay. So now I have the same box. That's supposed to be the same box. Imagine that looks identical. And now instead of a spring, I attach, say, a rope or a thick string. or some sort of a string that can support this mass. Are there forces being exerted on that mass by the string? And how do those forces look? How do those forces have to look? Well, they have to look identical to what we saw for the spring. There better be forces pulling down on equal sides. Look, if you want to replace this, right, you could always imagine inserting yourself into these situations. Imagine if you had that string tied to your waist and you were the mass, you would certainly feel that rope pulling upwards on you. Or imagine that you were up there and trying to support that mass from something tied to your waist. You would definitely feel that downwards pull of that string. So what's going on there? Why does that string present this force in the same way that the spring does? What's going on there? Well, let's come back to that idea and let's imagine a little bit more about a spring and see if we can't get our mind around that here. So the string we don't visually see when we hang the mass for it, it changes its size and there's this distortion in its shape like the spring. So why is the string providing a force? Well, let's imagine a different kind of spring that starts fairly open, something like this. And now what I'm going to do is I'm going to take and instead of pulling on the spring, I'm going to compress the spring. So now I take this thing and I'm going to squeeze on it until it's compressed into a small distance here, something like this. Okay, so maybe here's my hands squeezing on this thing, going back to a stick man that's here. I'm looking top down, saying I'm squeezing that spring from its original shape. What am I going to feel as I'm squeezing on that spring? What am I going to feel on my hands as I'm squeezing in on that spring?
Resistance from the spring and not be pushed down.
Yeah, as the spring is squeezed in, I'm going to feel an outwards push on both hands. Right? That push is a force. I'm going to feel a force. The spring is going to try to restore, right? The spring is trying to push itself back to its original shape. It's going to provide this outwards force. If I relax my hands, relax my muscles, don't provide a counter force, it's going to push my hands out. It's going to change their velocity and apply an acceleration. Well, springs come in different, what we call stiffnesses, and you're probably familiar with this, right? You could imagine making this same spring out of a very thin wire, in which case it would be very easy to compress, and if I relax my arms, it doesn't push it out very much. But a spring can also come in like a very stiff, rigid material, so that as I squeeze it, right, you've probably experienced this, as I squeeze the spring, it provides a lot of force, a lot of outwards push for just a little bit of squeeze, and I don't have to distort it very much. You can imagine that changing the properties, the material properties of the springs to a stronger metal or a thicker diameter wire can increase the stiffness. And you've probably experienced this with a spring. And it means if I try to pull or compress that spring that's stiffer, that it provides a harder pull, harder restoring force for smaller changes. So I hope we can agree that it's not the amount of squeeze or distortion that an object has that leads to the force, right? If we think about playing that idea forward of the stiff spring, if we made it very, very, very stiff, we could make a spring that's so stiff that I distort it, but it's imperceptible, the amount that I'm distorting. Even though I'm squeezing as hard as I can, it seems like it's providing a force to push back out on me, and I can't see it changing its shape. Well, the same thing is happening to the rope. Okay. At the smallest distance scales, there are atoms and molecules that make up that rope. And when I provide a force, I displace or I change ever so slightly the orientation of those microscopic material properties, and it provides a large restoring force. Okay. So you can think about most things, right? When I stretch or push on them, right? If I take my iPhone or something and I squeeze on it, it provides a strong restoring force. If I squeeze on it, it's preventing my fingers from this down, right? If I squeeze in, it has some velocity and then I get some outwards force, changing that velocity to a rest. And I can squeeze really hard without visibly changing the shape of my iPhone. But if I were able to look really microscopically, I would see that I am distorting the shape of that thing in some small amounts. It's just a very, very stiff, rigid object that provides a lot of force for a small amount of change. Hi, is everybody still there? I just saw a bunch of people fluctuate in and out of the meeting. Can people still hear me?
I think the whole internet on Shaka in the Shaka buildings just crashed for some reason.
Okay, is everybody back? Can folks hear me? Okay, I'm gonna continue. Looks like we have most people back now. Okay. So then so I hope that kind of helps you with the idea that forces come about from, right, on a macroscopic scale by changing or perturbing the shape of an object, and that object, right, at its smallest scales, the displacement of all its atoms and molecules, they like to go back to their original configuration because somehow they were in like some low energy state that they've been disturbed from, and they'd like to return to that. Let's talk about one more quick example then on my little sketch here. Let's think about just a table surface. So maybe I have a nice thick wooden table here, and it's sitting on the ground. And what I'm going to do is I'm going to put a mass or a book or a box and rest it on top of the table like this. So it's a box just sitting on top of a table. What forces are acting on this block? Can we identify some different forces? Gravity. So you guys have probably read and have experienced that near the surface of the earth, there's always this downwards pull from gravity, right? If you jump off from the ground, something pulls you back down to the earth. That's what we call gravity. We're going to call that the force of gravity. I'll usually use this symbol Fg to represent that. What other force is acting on that mass?
Normal force, the force that counteracts gravity.
Yeah,
Supposed to
and
be
a
equal in-
normal force. What is a normal force? Can we elaborate on that? Can someone else explain what the normal force is? What's causing the normal force? What's providing the normal force? I see Bailey saying normal force of the table on the chat. Right, the table. The table's pushing back up on this object. There's a normal force from the table pushing back up. Right, if that table suddenly vanished, then that object would get pulled down to the ground because it would be accelerated, right? Right now it's at v = 0, it's at rest. If the table vanished, then that force that the table's providing would vanish, and that would mean that there would be a downwards pull from gravity, and that would be the only force acting on that mass, and it would get pulled down and speed up towards the surface of the earth. Okay. So remember, we said a few things I want to point you to in this problem. We said early on, by thinking about the two people pushing each other, that forces always come in interaction pairs. Right? So the gravity, the force of gravity, is coming from the interaction of that box with the earth, with the entire earth. And normal force is coming from the interaction of the box with the table. And in the next chapter, we're going to really focus on this issue of identifying the partner objects that are generating interaction pairs. Why is that table generating that upwards normal force?
If I had to say, it's because the gravity is pushing down on it, and the molecules inside are not really want to move, so they're going to resist the push. and push it back. Is that right?
Yeah, that's right. The mass that's set on the table is deforming the table. Just the way that when I pull on the spring, it deforms the spring and the table wants to restore itself. We can run this too, right? Imagine that if I had a thin board, a really thin board, something like this, like maybe a ruler, right? Like a meter stick or something like this, a long thin board. And I'm holding on to that long thin board, say. So here's somebody holding on to this end. I'm gripping it. That's supposed to look like somebody's hand. And then what I'm going to do is I want to balance, or oops, shoot, I just erased that, my fault. I've got this thin board here and I'm holding on to it and I want to place a massive object, right? A mass on the end of it, something like this. Is it going to look like this? Is that meter stick, if I put a pretty heavy object at the end of that meter stick, is it going to look perfectly straight like this? Well, it's not. You can imagine doing this at home. What I'm going to find is to hold it with that meter stick, it's going to have some curvature to it because that meter stick is going to get bent by that mass. And the more it bends, the more of a restoring force is replaced. And so, right now there's a force being provided by the meter stick to counteract that downwards pull of gravity. So this is an example. You can see that wooden object being distorted by that downwards push of the mass, and it really bends, and after a certain amount of bend, it's able to provide the proper upwards force to counteract the downwards pull of gravity. Nothing is different about that and the table. Here's the tabletop with the table legs, and we put the box on top of the table. Why do I keep doing that? Sorry, guys. Table. I really want to push that clear button here. Box on the table. And even though the table doesn't look like it's distorting, if we were to measure with very precise equipments, what we would find is that that table is bending under the weight of that force. It's distorting the shape of the table. And so that means that the table provides an upwards normal force to counteract that downwards pull of gravity. You can actually do this on your own. And if we were live, I would do this for you in a classroom. If you just put a laser on a standard table and shine it at a point on a wall far away, and you make a mark, and then you stand and get up and stand or put something extremely heavy on the table, you'll find that that mark, that laser mark, moves because you distort or you alter the shape of the table. And when you're setting small objects on it, you're doing the same thing, but just in an amount that's imperceptible to you, so that it seems like the shape is staying unchanged. Okay. All right. Any questions about that? So hopefully what you see is that forces, right? Here's what I want you to take away from this discussion. Forces are pushes and pulls. Okay. You can have multiple forces acting on a single object, right? Like if I also had a spring strapped to this table that was pegged to the ground, the table could be pushing up, gravity could be pulling down, the spring can be pushing down, there can be multiple sources of forces. The forces want to change the velocity of the objects that the force is acting on. It wants to provide an acceleration. And macroscopic objects, typically, right, these normal forces that we're going to talk about, these hard interaction forces, come about because of distortions in the shape or the geometry of the object, for some sort of restoring force that the object provides. Now, springs are nice because we're going to see that springs have a really clear relationship between how you distort them and the restoring force they provide, whereas other materials don't, and we're just going to write down just like a force that they provide without talking about the functional form. But as you go through, if you do a formal kind of engineering mechanics class or force analysis class, you might get into the details of how those forces arise on more rigid objects from some distortions in their shape. So let me do another one here. Now let's think about a ball that's being held above the ground. If I drop this, if I have a ball and I'm holding there and I release it, what's going to happen? What's going to happen to the ball? Well, we all know it's going to fall, right? Yeah, thank you, Logan. The ball is going to fall. What does it mean that it falls? Well, it starts with v equals 0. And as it goes, we know now from our kinematics that as it goes, it's going to speed up, right? At some later time that it's going to have some v final that's not equal to 0. The ball is going to speed up as it's falling. We know that means that there's some acceleration acting on this ball, right? That's what we talked about for the last several chapters, analyzing the motion, the kinematics of an object. If the velocity is changing, it implies there's an acceleration. Well, what gets things accelerating? Okay. The things that accelerate objects are forces. If we think about all those examples we just looked at, right? If you're standing at rest, if you're just sitting there, standing there, the only thing that's going to move you is if a force acts on you, if there's a push or a pull. You can move yourself by causing your shoes to push against the ground, or somebody could come and push on you. A rope could come pull on you. That's the only thing that can disturb you from your initial velocity. Some push or pull. So that push or pull leads to an acceleration. Well, it turns out that not only do push and pulls lead to accelerations, Newton's laws say that the only thing that leads to accelerations are pushes and pulls, are forces. So we have this idea that a force generates an acceleration, but not only that, if I see an object that's accelerating, then it's experiencing a force. Okay, it goes both ways. This is why kinematics is so powerful, right? Analyzing an object's motion. If I look at an object and I say, gee, that object's velocity is changing as time goes on. It's accelerating. Well, now based on what we just said about forces, there's major implications to that. If I see an object's velocity changing, it tells me that it's experiencing a force. Something's pulling or pushing on it. And that's interesting because we know that that means something, right? There's a something to that. Something's pulling or pushing on it. So there's another object that's interacting with it. So as soon as I see an object in nature accelerating, I know that there's at least some partner that's pushing or pulling on it, and they're working together and providing accelerations. And I can use that to try to understand fundamental interactions of objects in the universe by observing accelerations. Okay. What's pulling on that ball? It's the Earth. The Earth is pulling down on that ball. Gravity is a weird force compared to the normal force, right? It acts over large distance scales. It's like this invisible rope that reaches out from the Earth and pulls you back down towards it as you move away from it. Okay. Now, if you go on to study particle physics, or you've read up on particle physics, what you actually find is that that is not so unusual, that forces are exchanged over some distance, but that it's actually the rule in nature, right? That if I zoom in, the reason I feel a push at my fingertips is because my fingertips are made up of small objects called atoms that are made up of electrons and protons and neutrons, and they're charged objects. And there's a rule that says that if I have two charged objects, say two electrons, and you'll learn all about those in 314, and I bring them very close to each other, that they exert a large force, a large repulsive force on each other. And they do that without ever physically touching. They exchange that force over some distance in a vacuum. So this thing that we call touching, this normal force, is really a realization of a lot of electromagnetic interactions of smaller particles. And all of those forces get transferred between the fundamental objects in the system without any real physical touching. It's just that distance that the force is transferred over for electrons in our fingertips is so small that we call it touching. I can't visibly see through that, right? It blocks the light out to our eyes, whereas gravity acts over large distance scales. Is there another example of a force that acts over a large distance scale that you're without where you can see the force being exerted without the physical touching over a macroscopic scale that you can see with your eye? Yeah, magnetism, Logan says. Right, that's another one. If I have two magnets, say a north and a south, and I bring another magnet opposite side or like sides together, right? It's hard to push those magnets together. They start resisting each other and they'll get stopped and provide this strong repulsive force as I bring them closer, right? They don't have to physically be touching, and you feel that repulsive force building up. Again, you'll learn about magnetism and the electromagnetic interaction in Physics 314 next semester. That'll be other examples of how these forces are realized over distance scales.
I have a side question.
Yeah.
So, okay, so I understand that technically nothing is ever touching, then how come we can feel the texture of things? Because like sometimes you can feel rough textures and
You're talking about your sense of touch. How does that work?
yeah, because like, you could feel a rough texture, but you can't touch it technically.
Right.
that
Well, you can imagine, right? I mean, why does that work? So, I mean, right, like like if I zoomed in to a rough surface, right? It might be jaggy, something like this, right? And then if I bring my fingertip down, let me get something, right? If I bring, this is my fingertip. Well, my fingertip is going to feel like the electrons in my fingertips are going to be pushed differently by that different undulation of the material at the surface, right? And so I'll feel that as rough because my body can detect, right? It gets transferred to my brain through a long process, all these like coarse undulations, right? Even though that's all happening with some gap there, right? And so a
Okay, that
smooth
makes sense.
surface means that right, that rough just means that it causes some undulation in my fingertips or on my skin that's not really perceptible to my eye, but it's enough that my nervous system can pick it up. Does that make sense?
Yes, that makes sense.
Okay. All right. So I want you to think about one other idea about this long range forces, right? There's one other example. Can anybody think of another way that you could transfer a force? Is there a way that you could macroscopically transfer a force over some distance to, say, a friend at the other end of the room that would move them in a meaningful way? Can anyone think of how that would work? How could I push somebody at the other side of the room or transfer a push to them?
Well, technically, if you put something in between you, the force in between you would then push the thing on your friend, I guess.
Okay, but something, okay, that you're absolutely right. If we had a rope between us or a stick or something like that, but then somebody would say, okay, well, there's this physical contact all the time. I want to transfer this force from one side of the room to the other side without a continuous physical contact between any parts of the system. Through the floor? No, that's a good idea, but no. That would still, right, if the floor would be like some continuous connection between physical objects. Any other ideas? Sound might be able to do it. That's a good idea. If you did a big, right, send out a sound wave, somebody blow a big horn and send it out. That air might push them over. Ah, Natalie, you got the one I was thinking of. Throw something heavy at them. Okay. Right. If I have person 1 and person 2 here, right? Person 2 could take a big heavy ball and throw it to person 1. They have to push really hard. What happens to you when you throw that big heavy fall? When you throw that big heavy ball, you feel like you get pushed backwards. There's a force acting on you, and that acts on the ball, and that causes the ball to go out. And then when this person catches it, he'll get pushed. He'll get pushed back. Right? So you pushed on a ball, gave it some speed. Then that ball is going to travel in a projectile motion over to my friend there, right? And then he's going to catch it, and he's going to then stop or change the velocity of that ball. And that means that he's going to experience the force. And that force is going to be the equal and opposite force to what I experienced when I threw the ball. So it's contact force, but it's not this continuous, right? Not this, it's not like we're making one rigid object that's getting pushed and back, but I exchange that force through an intermediate object. So in particle physics, right, at the fundamental level, we believe this is how all forces are exchanged. That two electrons, what they actually do to exchange a force is they throw a photon, they throw a piece of light between each other. And two small massive objects, the reason they interact gravitationally is they throw a little piece of gravity that we call a graviton between each other, etc. So fundamentally, the way particle physicists think about nature is that all interactions happen over some distance scales, and they all happen because one particle throws an intermediate particle to another one. And that causes an exchange of force, right? Transfer of momentum. We'll talk about momentum later. So really this idea of a normal force, right? Some people think gravity is very mysterious because it acts over long ranges. But when you go and you probe into nature, how things work at the fundamental level, in fact, forces acting over a distance is how all forces work. And they all work by exchange of some intermediate particle that's being thrown between the fundamental objects. Okay. Now, when we're doing force analysis in this class, we're not going to have to talk about, right? I mean, when we're talking about large macroscopic objects like humans and balls, we're talking about systems that are made up of uncountable number of electrons and, right, these subatomic particles. And we don't want to think about all these intermediate processes and small microscopic things that are happening. It becomes an untractable problem. So we're just going to assert that there's a total macroscopic force that we can assign to different objects and try to identify those. But what I want you to keep in your mind is that they're all coming from the interactions of all these collections of subatomic interactions at some level. Okay. Let me clear the pen. Let's do one more thought experiment, and then we'll be about done for today. So here's my guy, and what he's doing is he's holding a ball in his hand, and what he's going to do is he's going to take and he's going to toss that ball straight up into the air. Okay, so the ball is going to move up. We know that it's going to reach some maximum position. Okay, then it's going to turn around and come back down towards the earth. He throws the ball straight up. What forces are acting on that ball after it leaves my hand? What forces are acting on that ball once it leaves my hand? Okay, I see several of you saying gravity. Okay. And drag. Yeah, let's ignore air resistance for now. There probably is some air resistance causing some drag. Gravity, everyone's saying gravity, right? There's one force, there's this force of, let me get a different color. There's a force of gravity pulling down on that ball the entire time. Why? Because it's interacting with the earth. The earth is always there, and there's this long range interaction here. Is there any other force acting on that ball if we ignore air resistance than that pull of gravity? Once it leaves my hand, does my hand provide any force on that ball? The push of my ball of the push of my hand on that ball, does it provide a push while the ball is in the air or after it leaves my hand? No, that normal force stops acting as soon as the ball leaves contact with my fingertips. I see some questions in the chat. Would the ball push back on me? I think you mean as I'm launching it upwards, does the ball push back down, right? Let's say I'm holding it at rest, and then I'm shoving it up, so I'm changing its velocity, so I'm definitely providing a force. And indeed, the ball is going to be pushing back down on my hand as I'm throwing that thing up, right? If that ball wasn't there, I would be able to accelerate my hand up more rapidly, and because it's pushing down, it's actually causing resistance and slowing my hand down. So the ball, once it's free of my hand, right? There are these forces exchanged between my hand and the ball, but they stop as soon as the ball leaves contact with my hand. These short range contact forces only act when the two objects are in contact. Okay. All right. So, sorry, I'm just taking a look at my notes to make sure I went through everything I wanted to on this set of demos. So now I hope after that discussion, hopefully that sets the stage for some of what is happening here. Why can't I advance my slide? Right, some of what you read in this chapter. So real quickly in the last 3 minutes, let's just go over the summary of what are the important principles from this chapter. Newton's first law says that an object at rest will remain at rest, or an object that's moving will continue moving in a straight line with a constant velocity if and only if the force, the total force, the net force on the object is equal to 0. Okay. The simple way to say that one is that forces, okay, cause accelerations. If there's no force acting on an object, it won't have an acceleration, so its velocity won't change. So if it had a fixed initial velocity, it'll stay the same. If its initial velocity was 0, it'll stay the same. Forces are what generate accelerations. Okay. Your book says there's this idea of Newton's 0th law. That touches on this one with the ball leaving the hands, that when we're analyzing forces acting on an object, those forces are all, we're thinking about them all acting at an instant. There's no remnant of a force on an object. Once that ball leaves your hand and that normal force stops, that's it. The acceleration that would be provided by that force is done, and the ball is only responding to the forces acting on it in a given instance. Newton's second law is a quantitative expression of the relationship between force and acceleration. We're going to focus on this more tomorrow. It says that the force and acceleration are related to each other by the mass of the object. Okay. That mass is somehow a tendency or an ability of an object to resist a force. The more massive an object is, the smaller the acceleration on that object will be for a certain applied force. And we'll come back to this again tomorrow. Okay. So acceleration, right? You see that forces lead to accelerations. And if I see an object accelerating, it implies that it must have a force. And I could figure out what that force is through the mass. And so that links us immediately to the kinematics that we saw, right? We know how to analyze an object's motion to determine if it has an acceleration. And that means we can continue to use all the kinematics that we learned in the last chapter to help us understand what forces are acting on an object, to help us with our force analysis. Okay. Right. This is just a plot then that the relationship between the acceleration and the force tell us about the mass of an object. And at its core, right, we can think about boiling this all down to say that a force is a push or a pull on an object. We're going to focus a little bit more tomorrow on this fact that force is a vector. It has a strength and a direction. A force pulls in a certain direction with a certain strength, right? I can pull harder, I can pull softer, I can pull up, down, left or right. Force requires an agent. Okay? Something has to provide the force. It takes two players to generate a force, two objects interacting with one another. And your book says that force is either a contact force or a long-range force. I tried to clarify this a little bit, that the actual thinking is that all forces are these sort of interactions that happen over some distance scales. That distance scale just happens to be different for some kinds of forces compared to others. Like gravity, the distance scale over which it acts is much larger compared to that for the electromagnetic interaction. So we're going to practice tomorrow when we get back together. What we're going to do is we're going to look at systems, and we're going to start by doing force analysis. We're going to look at systems, and we're going to try to think about the objects that are interacting with one another and use that to identify the forces, right? The interaction pairs that are appearing in the problem. And then once we have identified those forces, we can think about how that might impact the motion or where the acceleration is coming in the problem. And the tool we're going to use to do that is we're really going to focus on this next chapter, but we're going to start by making some simple, what we call free body diagrams. We're going to imagine taking objects, reducing them to single points, and trying to indicate with vectors, because forces have size and direction, indicate forces as vectors emanated from a common point that capture all of the forces acting on that object. Okay. All right, we're going to stop there for today. We'll pick up right here. Tomorrow, we're going to go through a bunch of problems from this chapter to wrap our heads around this simple introduction to forces. I appreciate you sticking around for 3 extra minutes. That's it for today. I'll get the recording posted later this afternoon. And if anybody has any questions, I'm happy to stick around for a couple minutes here after class. Thanks so much. I hope everybody has a good rest of your day. All right, bye now.
Okay. Master Matthew, I've emailed you yesterday because I was having trouble with Pearson.
Okay. Yeah, I don't know that I've seen that. I'll take a look. Were you asking for some extension on your assignment?
Yeah, just like one of them, because like keep signing me off, so like I have to take pictures of all questions and then like solve them on a side, and then like just put the answers when I go back on the side, and then just close on me again.
Okay.
So
All right. I'll probably get to your email this afternoon when I'm going through my emails, and I'll send you a response. Okay.
okay, thank you.
Yeah, if you're having technical issues, I'm sure we can work something out.
Also something else.
I'll point out, Miriam, that you should be able to still, even though the assignment is closed, go on and finish up the assignment. And then we can work out, to open up and accept whatever you weren't able to complete.
Okay. Also, I have a question.
Yeah,
Like
go
if
ahead.
I solve some question, if I solve some equations, questions, yeah, from the book itself, can you like check it for me if I send it?
Oh,
Just
sure.
like to check if my answers are right or not.
Yeah, and I think a lot of the book problems have solutions in the back, but maybe not all of them. So if there's one that you want,
Yeah,
me to
just the
check,
odd numbers.
yeah,
Okay.
if there's one you want me to double check, I'm happy to do that.
Okay, thank you.
Yeah, you're very welcome.
Have a great one.
Yep.
Hello, Professor.
Yeah, Ricardo, what's up?
I just had a question over hot air balloons, because we were talking about contact forces and long-range forces, and I was wondering how like hot air balloons work, because I can't really think of a specific force that would make hot air balloons work.
Yeah, so a hot air balloon, right? So a hot air balloon works the same way that if I have a tank of water, right? Like, so maybe I should use blue. Right, if I have blue, something like this, a big tank of water here, and if I push, say I hold a tennis ball in this tank of water, well, that tennis ball wants to get pushed back up, right? There's this buoyancy, it wants to float in the water. And why is that coming about? Well, it's related to the pressure, but it's a contact force. Essentially, the particles at the bottom of this fluid are pushing against this against this object more strongly than the particles at the top are. So these guys at the bottom push harder against this than the ones at the top. There's actually like there's a pressure gradient across this thing, and we'll talk about this when we come to fluid dynamics, why that is. But essentially it has to do with, because of the stack of fluid there, the deeper in the fluid you are, sort of the more, right, it's because gravity pushes down, and when you're deeper in the fluid, there's more fluid getting pushed down, and so it responds with a larger push in all directions. The same thing is happening for a hot air balloon. Like your hot air balloon here is, you can think about like when you heat it up, the reason you're heating up the air inside of the hot air balloon is because you're making the air inside that hot air balloon less dense. So the density of the air is less than the outside air, something like that. So it's the exact same thing, that really your hot air balloon is in a fluid of air. When you remove that air out of this thing, then there's an extra push from that air outside the hot air balloon than there is above it, and it forces it up. So it's that the air is pushing against the balloon harder on the bottom than on the top. So the thing that it's interacting with is the air.
So would it be like a normal force, or
What's that?
would it be like a normal force?
It's not what I mean. We would usually call that pressure, right? Air pressure, because it's what you can think of is there's a bunch of fast-moving molecules that are banging into the sides of the balloons, right? Like little BBs ricocheting off the edge of the balloon. So that's kind of like you could think about that kind of like a normal force. Like there's a bunch of little air molecules that are ricocheting constantly off the balloon. And because of the way the air gets set up, and because it's set up in a gravitational field, the air molecules at the bottom of the balloon, right, as you go deeper into the air, are actually moving more rapidly than the ones above it. And it leads to that kicking, like basically pushing the hot air balloon up.
Okay.
Yeah,
thanks.
hold that question. I mean, it's a really good question. We are going to talk about pressure and some of these and how forces get generated from pressures in a buoyant force. So usually we call this the buoyancy or buoyant force. And you can think about it is like more like a physical contact force, because it's the air, right? It's the fluid that I'm submerged in that's causing this. And I think we come to this in chapter 14 or so. So we'll definitely talk about this more. It's a good question.
Okay, thanks.
Okay, you're welcome. All right, I'm going to go ahead and end the call. I hope you have a good day.
You too.
Okay, all right, bye.